This chapter is essentially about two different components of acids and bases. One is how to tell if something is acidic and basic based on its reactions, and secondly, we're going to be doing some calculations with it. This tutorial will just taking a look at how to classify if something is an acid or a base, and it's important not to lose sight of some things that we already know. Okay? An Arrhenius theory is how we explain what we see when it dissociates. So a compound of some kind, if it produces hydrogen ions, just free-floating ions of hydrogen, that would be defined as an Arrhenius acid. If it's a compound that will create a base, it would be producing hydroxide ions. Okay, so an example there, if we take a look, just a simple one would be something like sodium hydroxide. Okay, this would dissociate down into a sodium ion plus a hydroxide ion. Therefore, we would classify this as an Arrhenius base. So real simple, real straightforward with it. What would happen if that were to break down into its respective ions? Okay. Now, if we move forward into another definition is a Bronsted-Lowry. While Bronsted-Lowry theory explains what happens when a reaction actually occurs. So a compound that will give up a hydrogen ion is classified as an acid, and anything that will take that hydrogen in will become a base. So here we see an example of hydrochloric acid in water. We already know, after a full year's worth of chemistry, we already know that your hydrogen ion or your hydrochloric acid is an acid, but in this case what's happening is this hydrogen ion is moving into water. Okay, so let me get rid of some of these extra lines here. What's happening is the water will actually be accepting the hydrogen in. Okay, so the hydrogen is moving. We can see it forms H3O plus and the chloride ion. So what's happening is this hydrochloric acid is losing the hydrogen, and the hydrogen is going into water right here. This becomes the hydronium ion on this side, which means that it has an extra hydrogen in there. This would then be called an acid by definition because it gave up the hydrogen, and this would be called a base. Yes, water can act like a base if it takes that hydrogen in. It becomes H3O plus. So essentially, if I was going to reverse this reaction, this hydrogen would come off of the water here, and it would go back to the chlorine to become what's on the reactant side. So since it would give up, okay, it has potential to, so we call it conjugate. It has the potential to give it back, and so anything that gives up is called an acid. Anything that would take it in would be called a base. Okay, so chloride is a base. Now notice that whatever is acid on this side becomes the conjugate base on this side. Okay, so keep that straight. Now it's real easy when you see something like hydrochloric acid to spot if something is an acid or a base. But what would happen if we took a look at something like this? We have the ammonium ion, or ammonia, I should say, and ammonia reacts with water. The question is, how does it react with water? Well, look at the reaction, what's happening. We're seeing that this ammonia is actually going to be gaining one more hydrogen. So water is going to be losing a hydrogen and form the hydroxide ion. Anything that gives it up is an acid. Anything that takes it in is a base. So just in a Bronsted-Lowry theory, we're just seeing what happens. Now, this ammonia becomes ammonium. If I was to reverse the reaction, well, what has to happen is this hydrogen right here has to go back to water. Anything that gives it up would become a conjugate acid. Anything that would take it in is a conjugate base. Okay, so real simple and straightforward with that. Don't lose track of what we see. Just track the hydrogen. Now notice in both cases, water in one case is a base, in the other case is an acid. So you can't tell what one thing is going to be versus another. So what I want you to do is keep in mind that some things are going to be amphoteric. Okay, amphoteric means it sometimes acts as an acid, sometimes a base, and you won't be able to predict what's going to happen until you track that hydrogen. Okay, now, what about anhydrides? Well, anhydrides are what this thing will become. It's basically a synthesis reaction with water. What this thing will become. Now, it's a little deceiving when I show it this way because I already sorted it out. Here's what you have to do to kind of track what happens with the individual hydrogen ions. Okay, here's how I want you to record it. My board can start to cooperate with me here. All right. So make a synthesis reaction. I'm going to combine, I tell you that it's an anhydride. The question is it acidic or is it basic? So I have SO2. I'm going to mix in some water. I know I'm just rewriting what I put there. Let's make one big compound, okay, H2O3. Now I can factor out, okay, this SH2O3 doesn't look like anything we've studied so far. So what if I try to factor out a hydroxide? If I do that, I can make two hydroxides, but I'd still be left over with one oxygen. So that doesn't really make sense to us. Let's try something else instead. Let's put our hydrogen out in front. And there we should be able to recognize that this is actually sulfurous acid. And so sulfur dioxide would act or behave like an acidic anhydride. Now let's take a look at the example of sodium oxide. Okay, I'm going to mix it with water. Now I put here the ultimate answer, but let's look at what happens. I have Na2, I have two oxygens, and I have two hydrogens. So there's my compound, Na2O2H2. Okay, so if I put a hydrogen out in front, NH2, Na2O2, this doesn't look like any acid that I've ever seen before or we've ever worked with. So that's not a possibility. But what if I group them together, Na2, and then I group together my hydroxides? I have two of those. All of a sudden this looks like something that we've worked with before. In fact, I can reduce this and put a 2 out in front to become 2 sodium hydroxides. So based off of just adding water in a synthesis reaction, we end up with NaOH. So Na2O would be a basic anhydride. And those are the only skills that you need to have for this section, is to predict if something's going to be an acidic or a basic compound when it gets hydrated with water. Okay, so real simple, and you should be able to go with those. This is just one of those basic things that we need to keep in mind with our pH scale. When we're talking about acids and bases, there are some characteristics. We have a pH scale that goes from 0 to 14, 7 being neutral. This is just saying that if a strong acid is between 0 to 2, a weak acid is anything here between 2 and 7 essentially. This is neutral. And then anything from here to up to 12 is going to be a weak base, and 12 to 14 would be characterized as a strong base, just to give you a little perspective where things would fit in with a pH scale. We'll talk about what that actually means with pH and hydrogen ion concentrations and so on in another tutorial. So just kind of keep in mind amphoterics. We have to keep in mind how to do some of these predictions. And here's an equation, one thing that you want to keep in mind, that the concentration of hydrogen ions times the concentration of hydroxide ions will always equal 1.0 times 10 to the negative 14. So from here, just basically do some of those problems and you should be good to go.